Right, so I'm recording. So I'm just going to move myself out of the way, make myself a little bit smaller. I'll put myself down here. Well, no, I'll put myself here as well. Right, okay, so the first term to do with architecture is being able to explain what a CPU is effectively. So it's really important that you can say stupid things like it's the brain of the computer, um, but that's not, that doesn't say anything, it doesn't explain anything. What the hell does brain mean anyway? So it's the brain. I bet I can't spell brain. Have I put Brian? Is that Brian? Oh, that's brain. So it's the brain of the computer, but actually what it does, um, its whole function, its whole purpose is to fetch, decode, and execute. This is all it does. It's a pretty boring job, really. So execute instructions, and it's all about instructions. Don't ever say that we fetch data and execute data, because but technically we don't. We can only execute instructions. And it is part of von Neumann architecture that data and instructions is in the same format. So when you get asked about the features of von Neumann, one of the things that you can say is that, oh yeah, data and instructions are in the same format. They're just binary numbers. Okay. So yeah, so that's its purpose. In doing that, it allows us to run applications, because applications are just basically lots of instructions and some data that we process. Okay, so that's what the central processing unit. So being able to go from acronyms to full names as well is another important thing. So sometimes you might ask, what does CPU stand for? And that's important with all the acronyms, and there's tons of acronyms, isn't there? Okay, so that's its purpose, that's its role. It controls, sends signals to control of the devices. I might use a fatter pen. But it does that job. So it does the fetch execute cycle, but it does this job. I'm going to go for a fatter pen actually. It does the controlling of the devices by executing instructions. So humans provide the instructions that the CPU executes, and it just dumbly gets an instruction, executes it. Okay, right. The purpose of an input device. Oh yeah, that's nice. That fatter line. Purpose of an input device. So what we use input devices is, as their name suggests, and it's quite important that you get into like a habit of, if you're completely at a loss as to what something is, just try and think about the words that are used to describe it. So an input device, it's got to be something to do with input. It's a device, it's a piece of equipment. So it's an piece of equipment. Now, we're just talking in generally. I'm not giving an example. I could give an example. So it's a piece of equipment, hardware, generally, that provides input data. So it provides data to the computer. And that's really what it is. If you then go into specifics and you say, like, all right, for instance, a keyboard, that provides information about what keys, what textual data you want to put into a computer. You could say a web camera, like I'm using now up here, that provides pixel information, but it provides input. And then, so it's just giving the computer a set of pixels. It decides what it does with it. Okay, how it processes that, where it goes. Initially, it'll go into memory, into RAM, but it may be like in this case where I'm recording. It's being streamed, it's been combined with this background, which is another screen I've got, and it's been saved to a disk. So the interesting thing about input devices is they don't have responsibility of what happens to the input. They just provide it. They just provide it. So that provide is the key word. Provides the input. Right. I'm going to do this question because it's a really weirdly worded question, and even I had to look at it a couple of times. I might reword this one a little bit, I think. But let's just have a look at this one. It says, why does data not go to the keyboard or come from a VDU? Now, the first question there is, what does VDU mean? Well, that's visual, gold. I got onto the next word there. Visual display unit. That's what that stands for. It's an old term now. I haven't heard any. Everyone just says monitor or screen, don't they? So, but yeah, technically it's a VDU, visual display unit. Okay, so if you've got to read this one carefully. It says, why does data not go to the keyboard? Now, we're talking about a generic keyboard, not a fancy keyboard that's got LED lights and things on it. Because the keyboard is an input device, so it only needs to feed, it only needs to send information, data to the computer. A visual display unit, a basic visual display unit, only needs to receive data. So it doesn't need to send any data back. Now, when we get down into the nitty-gritty of all these things, like everything, because the keyboard is an input device, when we get into the nitty-gritty, it is not as simple as that, because I know on my computer now, if I press the caps lock key, it turns a light on. But actually, I can control those sort of things from software. So there must be actually a way of communicating back and forth with a keyboard. So it's not as simple as that, but we're talking at an abstract level. We're saying like, oh, well, it's an input device. It only needs to send data. And a VDU, so a VDU is an output device. And because it's an output device, it only needs to receive information. It doesn't need to tell us anything back. But you know this is not true. If you've messed about with PCs, you'll know that when you plug a monitor into a computer, it can tell you what the maximum resolution of that monitor is. And it needs to be able to do that so it doesn't like freak it out with signals that could destroy it. Okay, so yeah, there is communication back and forth. But in a traditional sense, a monitor is an output device, so it only needs to receive data, the image data that it needs to display. Keyboard is an input device. Same with a mouse or a trackball. Same thing. They're providing data because they're input devices. What's really interesting is it's a lot easier if you get asked for some examples to specify input devices, because there's hundreds of different input devices. But when it comes to output devices, it starts getting a bit more tricky to come up with those. Right. Okay. Anyone got any queries about that? That was a bit of a weirded question, but one thing that I will say is that you've got to get used to things like that, where you think, hang on a minute, let's double take that. I didn't get that at all. So try and break it down a little bit. If there's commas, stop at a comma and just think about the first bit, because that's what I had to do. When I read the whole sentence, it was like, do what? But when I broke it down, then it makes more sense. Okay, so the next bit, one of the really core bits that you'll get asked about again and again and again is von Neumann architecture, which is where we get the list of the registers. So we have got, there's loads of registers, and if you carry on and do this at A level, we'll look at more registers. But in terms of the basic abstract von Neumann CPU, so if they ever say mention the registers of a von Neumann machine, this is what they mean. So the first one, the one that we should always start with, is the program counter. The program counter, whose purpose is to hold the address of the next instruction to execute. So that's the program counter. So all these are essential for the fetch, decode, execute cycle. The next one, and I'm doing it in sequence of the fetch, decode, execute cycle, is the memory address register. So that one is used to select a memory location that we might want to read or write to. So that's the memory. I always put address as ADDR for short. So the memory address register. One thing that you've always got to remember about registers, gents, is that they don't do anything. They're just a memory location. As some of you have said in your notes, they're super fast memory storage locations, registers, and they are. There is nothing faster in the CPU. Cache is not as fast to access as a register. Okay, on modern CPUs like ARM processors and modern Intels, you might have 64 registers that you can use to store data in and manipulate. And once you can do that, you can write programs to take advantage of that to keep the speed up for your execution. Okay, the next thing, when we fetch data, so we select a location based on the program count and say, right, we're going to get an instruction. We put the address in the memory address register and say, select that memory location. We then get the control unit to say, oh, read from memory, and the data will arrive at the memory data register. So that is the memory data register. And the memory data register is our little friend that holds on to things that arrive at the CPU, and it holds things that are going to leave the CPU as well. So it's connected using a data bus. I'll put address. Don't know why I did that. Sounds weird. It's difficult to write something different to what you're talking, to be honest. Right, memory data register. Okay, there are two more. So the next one that you'll remember, and really these four are the main ones that you've got to remember, is what we always shorten to ACC, because no one can be bothered to write the full name, but it stands for the accumulator. The accumulator is really important. It's part of the arithmetic and logic unit that does all the calculations and does decision making for us. And it's used to hold temporary values. It's those that you have multiple of in modern CPUs. So a lot your Android phones and your iOS phones, they've probably got CPUs that have got 64 accumulators stored inside the arithmetic and logic units. Okay, they're quite important registers when you're doing low-level programming. The fifth register, which you don't need to know for GCSE, but it's an important part of the fetch execute cycle, is what we call the current instruction register. And its only purpose is to hold the instruction that we're currently executing. So most of them have got the word register in their name, apart from program counter and accumulator. Okay. Right, over here. The three internal buses. So these are the ones that are used during the fetch execute cycle. So the first one is the address bus. This is the bus, and a bus just is a transport system. So this is used to select memory locations. So what location in memory we want to access. The next one, he says, dragging his finger on the I don't know why I press control. The next one is the data bus, and this is how data travels to and from. So this transports bytes or bits to and from memory. So that's data and instructions. To and from the CPU and RAM. Okay, so when we want to fetch an instruction, we fetch it from RAM and it travels along the data bus and arrives at the memory data register. You can see what registers they're connected to because the names. The memory address register is connected to the address bus. The memory data register is connected to the data bus. Now, in order for the CPU to perform the fetch execute cycle, it's got to initiate all these steps. It's got to say read from memory. It's got to say transfer the program counter to the memory address register. And all that is done through the control bus. So when you get asked, so this is signals to make actions happen, whatever those actions are. So whether that's reading, writing, moving data from one location. So I'm just going to put from component to component. So that could be registers. So if we load a number that we want to add to something and we need to give that to the arithmetic and logic unit, it's the control unit that sends a signal down the control bus to say move that from the memory data register to the arithmetic and logic unit. Okay. Right, the next one. Describe the function of the arithmetic and logic unit. So, the purpose of it is to perform arithmetic, as its name suggests. I can actually spell arithmetic. So that is like add, subtract, multiply, divide. Depends what arithmetic a particular CPU can do. In general, all CPUs can add and subtract. Some can't do multiplication, weirdly. So you have to do multiplication using addition and subtraction. Same with division. Okay, but obviously more modern CPUs, they can do a lot. They can do floating point arithmetic, not just like integer arithmetic. So that's one aspect of what they do. But they also do comparisons, which is very handy because that allows us to do ifs. So that's decision. So that's like decisions. They also allow us to do logic operations. So that includes and, or, not, but it also includes things like shifts. Okay, so shifting bit patterns left and right to like multiply and divide by 2. Okay, so it does all these things, and it is really the arithmetic and logic unit that allows us to do interesting things. So we can do comparisons. Is one number bigger than another number? So you can do all your less than, greater thans. So that's like less than, greater than or equal to, all those, not equal to, all those sort of things. Okay, let's move down. Got 3 more to go. Right, okay, so this one is a question that they ask quite a lot to do with performance, features of CPUs. And 2 main ones are clock speed. So with the clock speed, that controls one thing. So that determines how often the fetch execute cycle runs. So if you lower the clock speed, the fetch execute cycle will run slower. If you increase the clock speed, then you will increase the number of times you perform the fetch decode execute cycle. So it's quite a raw thing, So if you have two identical CPUs, one's running at 1 gigahertz, one's running at 2 gigahertz, then really what you can confidently say is that the faster one will perform more fetch decode execute cycles. It doesn't mean that it's necessarily going to run quicker, okay, because that comes into lots of other elements to do with how programs are written, how well they're written, whether they can take account of other features like multiple CPU cores and things like that. Okay, so that's what the clock speed. So if you increase it, you get more fetch X cycles. Okay, cache. Cache is an important one, remember. So with cache, you've got the CPU, you've got cache, and then you've got RAM. So in general, all our programs that we're currently executing and all the data that we're currently processing is stored in RAM. But it's quite a distance away from the CPU. Okay, so what we have is this system called cache, which is super quick memory. It's very close to the CPU often, and we've got to generalize a little bit here because there's different types of cache, but often we're talking about cache that's on the same silicon chip with the CPU. So it's very, very, very close, okay, millimeters away from the CPU. So the time taken to access the cache is quicker than the time taken to access RAM. Okay, we don't need to know how the hell this works because it is quite complicated. But as far as we're concerned, it runs faster, but it's also closer. The only problem with this is that it's the size. So it's always less in size than RAM, obviously. So I might have so on my actual laptop that I've got now, I've got 32 gigabytes of RAM, but I've only got 8 megabytes of cache. So there's a massive difference in the amount of data and instructions that I can store. But if we have our programs written well and they can take account of the cache that we've got and they're organized in certain ways, we can try and keep the CPU accessing data that's stored in the cache. So the more often that we hit the cache for the information that we want, the instructions and the data, then the quicker the CPU is going to go. As you know, with virtual memory is even further removed. And actually, the CPU can't access the secondary storage directly anyway. So that's why virtual memory is even slower once you start using virtual memory, because you've got transfer. Each one of those arrows is transfer. So you can see that if we wanted to get them from secondary memory, we've got to go all the way, get it loaded into RAM before we can access it. If it then ends up in the cache, then we'll be able to access it quicker. But there's multiple steps there. Okay, so the more often that we access the cache, the less time that the CPU is waiting, because it is the fetch phase of the fetch execute cycle which is the longest. Okay, the fetch takes the longest. So fetch is the longest operation. Because you can't execute your data until you've got all your bits of your instruction and all the things you want to do. Okay, so what we're trying to do is we're trying to speed that up. Cache speeds this up. Speeds the fetch up. Because we don't have to wait as long. Cache can be up to 10 times quicker than accessing RAM. So it's quite important. it's why when you're buying a CPU and you look at, wow, why does that cost a lot more? It'll be because the ones that are super expensive have got huge amounts of cache. Well, I say huge, but relatively huge. The difference between a CPU that's got 1 meg of cache, level 1 cache, and a CPU that's got 16 meg of level 1 cache is huge. It takes up a massive area on the silicon cache. Okay. Right, Bootstrap Loader, a boot program. Now, a lot of you have, from looking at your notes, a lot of you have got this nailed down. You know what this is. So this is stored in ROM. And we store it in ROM because ROM's non-volatile. So when we turn the power off, it doesn't lose anything. Its purpose, it's got a couple of purposes, not porpoises. Its purpose, it initializes and checks hardware. And you often see this when you turn the computer on. The default is to do a post screen where it tells you the status of the hardware. Often you can make it do a full memory check if you're having problems with your memory, but that takes ages. So most people have that turned off by default. So it initializes the hardware. Then its second job is to locate the operating system. So it'll search where you tell it to. And in general, we say, look on secondary storage, the boot drive. But you can change that, and you can boot from USB. If you've got like a recovery disk, that's when you would do that. You can actually boot from things like network devices. So you can actually boot from a server, which is quite a useful thing. Obviously, the big security problem there. So you have to be careful at using things. But it is quite handy if you've got your own network so that you can boot up from a central operating system. So it locates the operating system and loads it and starts to load it. It's why it's called a bootstrap. So the reason it's called a bootstrap is because it loads a little bit. And then that bigger program, so you know when you turn on a computer and Windows and you get the Windows thing at the start, what's happened is the BIOS program, the bootloader, has loaded that initial Windows executable, and then that takes over and goes, right, well, Windows is really complicated. I'll load all the other million components, and I will start loading those. Thanks for that. Thanks for setting all the hardware up, Mr. Bootloader, and thanks for locating me and activating me. But I'll take over from here. Okay. So it isn't the boot program of the operating system, but it locates the boot program. And we store it in ROM because we need it when we turn the power off. Otherwise, we won't be able to do anything with the computer. You know, if you didn't have a basic operating system, which is what the BIOS is, you'd have to put a program in at the start somehow. We don't want to go back to those days. Right, okay, and then the final bit is these terms. So these terms depend on what you're talking about. So when we're talking about storage capacity, so we mean how many bytes can we store, don't we? So that's why we say, oh yeah, I've got a 2 terabyte SSD. I have actually got a 2 terabyte SSD in this laptop. I've actually got one in my PS4 as well. Don't know why. I haven't got 2 terabytes of games on there. So that's how many bytes that we can store. The cost per byte, we often talk about costs because when we're talking about whether it's a storage device like secondary storage like a hard drive SSD or whether it's RAM, we're talking about gigabytes now, aren't we? No one talks about megabytes of RAM anymore. So we often do that cost per gigabyte, and that allows us to compare, doesn't it? So cost per gigabyte. So I can compare the relative costs. So one thing you always get asked about is where does a hard drive better an SSD? Because really an SSD just like runs all over a hard drive, apart from one thing. Hard drives are cheaper per gigabyte. You can now get like 16 terabyte hard drives. You can't buy a 16 terabyte SSD. You just can't do it. Once you start getting above 2 terabytes, they're incredibly expensive. And they're not making them any sort of sensible volumes that the price is going to come down. So yeah, that is the only thing that a hard drive wins on, really. SSD trounces it in every other department. And then when we're talking about access speed, we should always split that up. So we should say read speed. So how quick can we get data from the device? But we should separately talk about write speed. Because it might be that you can find a device that is really slow when you read it, but it's got blindingly fast write speed. And it will be, depending on what your application is, that might be okay. So if you want something for a video camera, you want something that can write incredibly quick. You don't care if it takes a little bit longer to read it back, because in general, the main action you're going to be doing is to be writing image data to the device all the time. So the read back speed don't matter. The write speed is critical. Okay, so you always, when you talk about, I put access there, I didn't mean access, I meant speed. So when we're talking about speed, always try and think about the context of the question and think about, is read the most important or is write? And we talk about them separately. Okay. Right, so registers in terms of CPU, so we're nearly there. Hopefully you got some of these main elements out. Those people that have good notes will have been all right with this. Right, so register is a ultra-fast storage location inside the CPU. They often have got a specific purpose, apart from the accumulator. Ultra, I put ultra storage, I didn't put quick. Okay, cache is just high-speed memory. So that's high-speed memory. And RAM is our working memory. So anything that we need to currently process, so that's active programs, and active data. Remember, it is the RAM and all the other forms of primary storage that the CPU can access. Anything that's in secondary storage, the CPU can't see, so it can't directly process any of that. So that's why we call it working memory. Right, okay, gents, I'm going to leave that there. I'll stop the video in a sec. So there's the overview. I'm going to grab that image and post it into the team chat. Yeah, I'll stop the video now. Hang on a sec.